delegates and participants, a very good morning to all of you. We have learned interesting and knowledgeable facts on SMT Lab, RNS instrument, recent trends in RF and microwave test applications, along with the interesting session on antenna and RF design issues in the RFID technology. Proceeding further, may I request Mr. Suvrat Verma from Rohde Schwarz to discuss his views and share his valuable experience on RF measurement systems, principles and operations. Mr. Suvrat Verma. He joined Rohde Schwarz in 2008 as a business development engineer in the radio monitoring and radio location department, dealing with passive interception and analysis of hostile communications. During this duration, he worked in association with the IF Command and Communication Center. Since 2011, he has moved to the Test and Measurement Department and is now responsible for educational institutes and research labs along with the non-telecom private customers in the northern India. Provided the necessary telecom commercial support in formulating and setting up of the EMC lab at the Government Engineering College in Delhi. Apart from the RF and measurement customer support, he has assisted leading NGO Center for Science and Environment working in the field of environment, pollution, testing to select the right solution for the testing of RF radiation and thereby evaluating its effects on human health.
Thank you, ma'am. So thank you, ma'am, for this introduction, and thanks to all of you who are present here in this Sunday morning to learn about this RF measurement. So today my topic would be basics of spectrum analysis. So yes, last evening my colleague Mr. Vivek discussed the vector network analysis and antenna design little bit, and we tested some of the antennas with some of the faculty members had it over here. So today we discuss very basic thing, which is spectrum analysis. Many of you must have used the spectrum analyzers, oscilloscopes, and today we will discuss this spectrum analysis, how this spectrum analyzer works, and first of all, why do we need it? Because we already have an oscilloscope and we generally have it in all labs, not these spectrum analyzers. So the difference lies in here that oscilloscopes are very near to like our thinking, because what do we measure and how do we measure is mostly a event of time. So in oscilloscopes, we measure in the time domain. However, in the spectrum analyzer, we make the measurements in the frequency domain. As you know that for the Fourier transform, we can convert the time domain to frequency domain, because every time domain signal is composed of multiple frequencies and with defined amplitude and phases. So at times when we need to have distortion, we need to check the proper content of signal purity, then we have to do the spectrum analyzer. So it is mentioned over there, sinusoidal signal in frequency domain looks like a triangular pulse instead of a sinusoidal wave on the spectrum analyzer of this oscilloscope. Okay, so the types of measurements that we will be covering over here are, of course, the frequency, because this is a spectrum analyzer, power associated with that particular frequency that we are going to test, the spectral purity of that pulse or that signal, and distortion, and most importantly, the noise. How much weaker signal a spectrum analyzer can detect, it depends on the class of the spectrum analyzer. Then we also will look into these spurious emissions, that what all emissions are there along with the desired carrier. Then we will see that how scalar network analysis can be done. It's different from vector network analysis only in terms of phase. The spectrum network analyzer gives us the phase, while here we get only the magnitude. So spectrum analyzer stays relative. Then we have noise figure measurements and phase noise. Also harmonic measurements, Then we have another interesting field called EMF, RF radiation testing. Here we will check with the help of an isotropic antenna that how we can test those fields and evaluate its effect on the human health. It's like it is a current topic in which people are concerned at how these BTS are affecting our health. So in this case, we can also use the spectrum analyzer, not network analyzer. And then all the analog modulation as well as digital modulation depending on the type of spectrum analyzer, whether it is a spectrum analyzer or a signal analyzer. The difference between these two is that when we say spectrum analyzer, it does the spectrum analysis for the analog signals. But as and when we say signal analyzer, it means that we are going to analyze the digital signals. Then last thing is the electromagnetic interference. So this lets us know that how our device is affected by the other electronic device, EMS or EMI, what all unwanted emission this particular device is making. So in this application also we have to use the spectrum analyzer. So these are the basic measurements that we can do, and like each point can be explained in greater details. We can be explained into one day. So basically, how does the RF spectrum look like? So generally, if you see the screen, it looks like quite like this. So we can see some peaks at around 75 megahertz, and then some adjacent peak in the VHF band. Now, how we implement a spectrum analyzer? The idea is not to design a spectrum analyzer, but to know that what all are the components of a spectrum analyzer and how these components, accuracies, inaccuracies affect our measurements. And basically the settings, how do we make the settings so that our results remain accurate as possible. So first is that it says that there is an input signal. It may be an N port, it may be a connector. You connect it via wire through a signal source, or you connect it directly an antenna. You get an input signal, and then it is attenuated, because signal analyzers cannot take power of the magnitude of kilowatts. It has to be in the dBm range. And then we attenuate it, then we pass it through a preselector filter, and now the main thing begins. That it has to be converted into the IF, so that further processing of the signal can be carried out. So the mixer is a very important, plays a very important role in this thing, and also the local oscillator. Below that local oscillator we see a crystal reference oscillator. It plays a critical role in the frequency stability, frequency accuracy also. And then this local oscillator is fed back to speed generator, which continuously gives these. It is a variable oscillator that can be used to tune to the particular frequency range. So we implemented multiple of mixers to get to the desired IF. Then another is the IF gain. Whatever IF we have obtained, we amplify it. Then the resolution bandwidth. We select a small section of the signal, not the entire spectrum for analysis. We select a particular frequency and the bandwidth around it, and then we carry out the measurement. Okay, fine. And then this is again amplified by the logarithmic amplifier. The purpose of this amplifier is basically to amplify the signal, which is the feeblest one, the weakest one, and the strongest one. So it gives you the display over the screen. One signal may be this much weak, and the other will be this much high. So all of these have to be presented on single screen. So that is what the role of the logarithmic amplifier. And then we have the video filter to smoothen the trace. And then finally our display. So we will discuss all these components, these main important building blocks, in little detail, so that we have an idea of how they are affecting our measurements. So I believe by now it is clear that the spectrum analyzer is doing the measurements in the frequency domain, and oscilloscope is a dedicated device for time domain measurements. Fine. So we know that it is sinusoidal signals, and the RF is coming from the input of the spectrum analyzer, and then another, the local oscillator is generating a particular frequency as wave, and then the multiplication of these two sinusoidal waves results into FRF minus FLO and FRF plus FLO. This would be the ideal situation, but we also get FRF and FLO. This is undesired, but we get it. So the value of the component which is suitable for our IF bandwidth is taken, and we further carry on the analysis over it. Fine. we always see that this RF is having some modulation content. So the side bands are represented by this red triangles on the either of the output level. The level of the RF that is being controlled by the RF attenuator and this oscillator defines that how our measurements are going to be affected. So here we say that 1 dB compression point, IP3, previously dynamic range, cross modulation, etc. all arise due to the level of these signals. And this defines our dynamic range, that how accurately we can detect a signal over the spectrum analyzer screen. Allow phase noise. So this oscillator is again not the purest oscillator available, but we have to make some compromises. So this oscillator does not only radiate the particular frequency but some other undesired frequency band, and which acts as a modulated signal, and we refer to as this SSB phase noise. So this phase noise is always there in any type of oscillator we are using, but the minimum it is, the better the results would be. Okay, fine. Because this spectrum analyzer is operating in a wide frequency range. So depending on that, we have to use a variable LO so that we can down convert all the signals and analyze the IF. How? One may think that, okay, for this 80 gigahertz spectrum analyzer, we will do all the IF conversion in one stage, but that is not possible because of the image frequency rejection. So we have to use a multiple of mixers, and finally we arrive at the lowest IF of 21.4 megahertz, which can be further processed. And these all IF at times are available for further use. Means there are exit ports from which you can extract this and you can use it for your own purpose. So 3.6 megahertz. Likely we implemented stages of these mixers so that this IF is brought down to the level which is suitable for the electronics to operate. Always there will be some frequencies which are undesirable, but we cannot avoid them. This will always be present. Fine. So we know that this FIF is the result of FLO plus FRF. So in case we need to tune this is just a small thing to show that okay, how we can accurately determine that the spectral analyzer is tuned to the zero span. So we just put the FLO to 0 and then we get this particular span, and then the frequency accuracy is corrected. 0 hertz marker basically. Now we go into the little detail of this block diagram that we have checked earlier. So this basic approach says that okay, we have a band pass filter, then an envelope detector, a peak detector for the display, logarithmic amplifier, and so on. We'll discuss these stages now. So what is the role of the band pass filter? The IF that we have got should be 21.4 megahertz for that particular case if we have. Okay. Then we put it to the RBW. RBW is used to, when we have got the IF, it is having a little bandwidth. We want to analyze a particular signal in that. We keep on minimizing the resolution bandwidth to separately see the two distinct signals. And that is done after the band pass filter and the amplifier. Now we see there can be filters, this IF filter, or it can be analog or digital. So the analog filters are preferred when we have like higher resolution bandwidth, while digital can be very narrow band. So when you have to make very accurate measurements, you want to very effectively select a particular frequency, then very small bandwidth, then we go with the digital filters. So we can see this 1 kilohertz analog filter is like quite wide, but 1 kilohertz digital filter is quite narrow. And that is what is required by us. Low IF filter, low IF filter, better resolution, and of course the noise decreases because the noise component is always removed because of this filter. Then again this logarithmic amplifier, peak detector. This logarithmic amplifier, as discussed earlier, it is used to depict the small signal and the bigger signal on the same screen. Its purpose is only this. Then we say, what is the role of the peak detector? It can be any sort of detector. See, when we say that, okay, the span on this screen is say 100 megahertz, and so the screen gets divided into the points are 100. So every point is carrying 1 megahertz of the bandwidth. And we want to know that what is the minimum, what is the maximum level, for example, in this peak detector. So we can always select the detector, and that, but within that bandwidth of 1 megahertz, we can select what is the maximum value. So the purpose of detector is only this, because in some spectrum analyzers we cannot always select the number of points. The number of points defines the accuracy of the measurements. So this is the purpose of this particular detector. Then video filter. Video filter is used to minimize the sort of, it is used to fine tune the spectrum rather. So when we say this video bandwidth of 2 megahertz, you see the spectrum is quite coarse, the green color. Then we say minimize the video filter bandwidth, and then the spectrum at 200 kilohertz, the spectrum becomes little finer. And when we say the video bandwidth should be 20 kilohertz, the spectrum has become the finest. Okay. But it should not be confused that it is the DANF. It is not the noise floor of the spectrum analyzer. It is just smoothing of the display. It is not related to the sensitivity of the spectrum analyzer. Now we say that, okay, we have discussed this resolution bandwidth, video bandwidth, and the sweep time. Of course, the spectrum analyzer takes some time to go from f1 frequency to f1 plus n. Right. So we say, okay, fine. We tune it to, we say this span is given by the green color, means in f1 frequency to f2 frequency. The time taken from traveling from f1 frequency to f2 frequency is called the sweep time. Then we have the center frequency given by red color and the reference level. So what I must tell you about the reference level, that whatever signal we are going to analyze on the spectrum analyzer are always known to us. In most of the cases, the spectrum analyzer deals with known signals, not with unknown signals. The level of the signal is known, and to prevent this 1 dB compression, we should be setting the reference level of the spectrum analyzer 10 dB above the expected signal level. So this prevents the spectrum analyzer from going into saturation. We say that we should keep the level of the reference level of the spectrum analyzer 10 dB above the expected signal level, so that it is not driven into saturation and these undesired components can be avoided. And this small button, the gray button, shows the coupled function. So next slide will let us know that why are they called coupled function. Resolution bandwidth, video bandwidth, sweep time are all coupled together. So the finest resolution bandwidth you make, the longer the sweep time becomes. Same is true with the video bandwidth. The minimum bandwidth you take for the video bandwidth, the sweep time becomes high. But if you want to get an idea of what the spectrum looks like, you should keep the resolution and video bandwidth to the highest. You get the idea, and then you keep on minimizing the video bandwidth as well as the resolution bandwidth. In the sweep time, you can analyze it in greater detail. But for getting an idea, you should keep those values, the above two values high. The sweep time becomes high. Yes. So now this is one formula to say that how this RBW influences the sweep time. So it is like the RBW 1 times increase is like to be n square times of increase in this sweep time. While video bandwidth is directly proportional to the sweep time, so the much you increase the video bandwidth, the much the sweep time increases. But in case of resolution bandwidth, it increases by the square of that value. What it says is that the variation of RF attenuation, which is at the input of the spectrum analyzer, should not result in change of the signal level. It should only get you more sensitive results. The more you attenuate the results, the noise is attenuated, not the signal level, if it is operating properly. Otherwise, you have maybe some wrong settings. Narrow band signals will be detected by any type of detector, as they show the RMS value, and even with any video bandwidth, you can get the signal properly. Okay. Again, there are some words of caution that change in resolution bandwidth or video bandwidth or sweep time, if leads to the change in the level of the signal which is being analyzed, that means that signal analyzer or the spectrum analyzer is going into saturation. Such should not happen. And similarly, the level of the signal, if we had put on the attenuation and the level changes, again, that means that the signal analyzer is operating in the saturation. We should correct the reference level immediately. Last thing, in changing this sweep time, if we change the sweep time, there are also functions available in which we can change the sweep time of the spectrum analyzer for quick measurements, and the level of the signal keeps on fluctuating. That means it is not getting sufficient sweep time. It should be set at a proper value, or rather we fix in the stop frequency, start and stop frequency, and let the spectrum analyzer operate on its own. Then we get the correct results. Okay, this only mentions what are the limits, like it can go to the thermal noise floor, it cannot go below the thermal noise floor in any case, it's an electronic device. It deals with real impedances and room temperature and a bandwidth of 1 Hz. We cannot bring down the resolution bandwidth below 1 Hz in any case. The finest resolution bandwidth available is 1 Hz. Best possible case. Okay. So we say that we can resolve two signals. The two signals may be closely placed by, and we have to resolve them. So the resolution filter should be as good as possible. Okay. And here it shows the AM signals. Let me tell you one thing over here, that through FFT it is possible to see two signals on the same frequency with different levels. It has been done by some software like persistence mode. We operate that, and through this we can see the two signals on the same frequency with different levels. However, in conventional spectrum analyzer, you can see only the signal which is at the higher level. The lower level signal would be just so here we see a measurement of AM signal, the modulated AM wave, and we demodulate it, and we see that how the sidebands look like. So we can also do this in the hands-on. We can generate an AM modulated wave with different modulation depth, and we can see the sidebands in the spectrum analyzer itself. This is one screenshot from the spectrum analyzer we already have in here. So this shows the carrier and then the two sidebands. And this spectrum analyzer says that okay, you can measure it with just press of a button. You just press amplitude modulation and it does everything automatically. You do not tune the markers to this different peaks. It does it automatically. Then the next thing is the phase noise. We know that every oscillator is giving out the intended frequency and some spurious emissions from it, and that led to the phase noise. And that can also be evaluated while you are developing a local oscillator yourself. So in that situation we say that okay, the spectrum analyzer phase noise should always be better or say lower than the device you are going to test. It's like common sense. So here we see a device under test, this the upper spectrum, and this analyzer's phase noise is well below it. So you can always analyze the phase noise of that oscillator that you are going to test. Otherwise, if the device that you are going to test is better in phase noise, then the spectrum analyzer's phase noise will take over and you will not be able to get what your device is like. economic generator, you can see that it is quite high. It is defined in BBC, reference to the carrier. Okay. Harmonic distortion measurements. The harmonics are always generated whenever we make all the measurements, and we can see that these harmonics are displayed by different marker settings. M1, M2, M3, M4. Like 6 markers can be placed, and beyond that 6, the harmonic level will be so low that it is of no interest to us or the application. So the first, the second, third, and fifth harmonic is like more than sufficient to measure. And also, this spectrum analyzer has the capability to give you the total harmonic distortion just by the press of a button. So you need not do the complex mathematical formula to carry out this. It gives you the values in percentage right away. Okay. Then these are the channel power measurements. We can define it. Means, for example, there are some people who are interested in telecom measurements. So they can just the masks are already set for a particular standard at how much bandwidth that particular signal occupies, and you can always say, just tell me what is the channel power in that particular bandwidth or the occupied bandwidth where the 99% of the power is transmitted. So you can just press, okay, I want this setting for GSM, and let me know, or the wideband technologies. You can just press the button and you get to know that what is the occupied bandwidth by that particular signal in terms of how much power it transmits. 99% of the power it transmits in that particular bandwidth only. So that can be readily displayed. And then also when you are defining your own masks. So masks come into picture when you design something of your own and you want to analyze it. So you always put a threshold that this device should be this much accurate, and you define those values. So you can always, this line in red above the yellow, if you can see from behind. So this defines that if the value crosses beyond this particular threshold, then the device fails the test. So this line can always be put in the spectrum analyzer, and you can carry on your testing in rather automatic mode. So that if the values are below this level, then it is fine, otherwise it needs to be redesigned. And then we say that, okay, vector network analyzer is one thing, and then we have this spectrum analyzer, and we can also do this scalar network analysis. For example, when we have a filter and we want to analyze that, okay, what is its pass band, so that we need not depend on a vector network analyzer. We can do with the help of a spectrum analyzer as well. And for this situation, we should have a spectrum analyzer with the tracking generator. So tracking generator is nothing but a sweep signal, continuous wave, without any modulation, of course, and that is being fed to the device under test one end and to the analyzer. So you can very well see what all band it has attenuated, and you can put the spectrum analyzer on sweep. The sweep signal is generated from the tracking generator. It goes into the DUT, and DUT gives its output to the spectrum analyzer. So you can see that what all is the pass band of this DUT, the filter, and what is the reject band, which is not visible over there. Similarly, you can do the return loss testing with the help of a VSWR bridge, because you need to have the reflection going back. Okay. So that was a little bit on the spectrum analyzer. We will discuss the important parameters of the spectrum analyzers in detail in the coming slides. Now we move to the power meter, because last night somebody asked me that do we need to have the power meter when we are using a spectrum analyzer? Yes, of course you need to have a power meter also, or rather say power sensors, because